Let's talk a little bit about interest, and in particular compound interest. Let's say you deposit an initial amount in the bank of $100, and we'll call this P for principal. And let's say the bank gives you an interest rate of 5%, which you're probably not going to find in any bank, but we can dream. And let's say that this is the annual percentage rate. Okay, so how much are you going to have after 1 year? So your new total is going to be the amount that you started off with, so 100, plus this 100 multiplied by the interest rate. In other words, it's going to be 100 times 1 plus 0.05, or your principal times 1 plus the interest rate. Pretty straightforward. Now, let's say that instead of compounding annually, it compounds twice a year or semi-annually. How is the math going to work on that? Will we actually come out ahead or behind? So in this case, we have the amount that we started off with, and now after 6 months, this amount is going to be multiplied by half interest. Okay, and then after another 6 months, this whole amount is going to be multiplied by half interest, since this whole amount is now our new total. So this is 100 plus 100 times 0.05 over 2, and now multiplied by half interest. This is going to be 0.05 over 2. Okay, let's simplify this a little bit. So this is equal to 100 times 1 plus 0.05 over 2 plus 100 times 1 plus 0.05 over 2 times 0.05 over 2. We can further simplify this, seeing that we have two common factors here. And now this is going to be 100 times 1 plus 0.05 over 2. And we have one of these here, and then we have the other one multiplied by this. So that's 1 plus 0.05 over 2. And look, these are the exact same thing now. So we can simplify this by just saying that thing squared. So this is 100 times 1 plus 0.05 over 2. Let me make this a little bit nicer. Squared. And just plugging in some numbers, or plugging in some symbols here using the same convention as before. This is equal to your principal times 1 plus the interest rate over the number of times we compound, time to raise to the power of the number of times we compound. So I'll just add that up here. N is the number of times the interest is compounded in 1 year. Pretty straightforward. Now let's say you have this in the bank for not 1 year, but let's say 2 years. So this is after 1 year. Let's say after 2 years. Let's see what this looks like. So our total is going to be the principal times 1 plus r over n to the n. This is after 1 year, but when interest is charged or given to you after the second year, it's evaluated on this new total that you got after 1 year. So this is now going to be multiplied by 1 plus r over n to the n. And the reason is this is now our new principal. I'll call that p prime. Okay? And simplifying this, we can see that this factor shows up twice. So this is just the principal times 1 plus r over n to the 2n. Now, this is after 2 years. Let's say we wanted it after t years. So pick a color here. After t years, we have the total is the principal that we start out with times 1 plus the interest rate over the compounding frequency times, or raised to the power of the compounding frequency times the number of years. So just as a refresher, P is the principal, R is the annual interest rate, N is the number of times it's compounded in 1 year, and T is the number of years. So why is it advantageous to have interest compounded? Well, the reason is, as you've seen here, let's say your principal is compounded semi-annually, so twice in 1 year. So after the first 6 months, you're going to get half the interest, half the annual interest rate applied to that, which is going to give you a slightly bigger number than you started out with. And then at the end of the next 6 months, in other words, at the end of the year, you're going to get half interest rate on that new total, which is higher than the amount that you started out with. So compounded interest is advantageous over non-compounded interest because it gives you interest on your interest. And extrapolating that forward, the more frequently you compound your interest, the more you're going to make. Let's take this to an extreme example, and let's say that interest is compounded infinitely often, and we call this continuously compounded interest. Okay, so in order to figure out how to calculate that, let's take the expression, this general expression that we had before right here. And n was the number of times that the interest is compounded every year, but we want to compound it infinitely many times. So we're going to take the limit as n goes to infinity. So now our total is going to be the limit as n goes to infinity of the principal times 1 plus r over n to the nt, just carrying over what we had before. Okay, now this p is a constant. This p is the amount that you start out with, so we're going to move that out in front of the limit. So this is going to be p times the limit as n goes to infinity of 1 plus r over n to the nt. Now let's do a substitution to make our life a little bit easier here. So let's let m equal n over r. So what is this going to mean? This now means that we take the limit as m goes to infinity. And because n was going to infinity, and if n goes to infinity, then we know that m also has to go to infinity. And furthermore, we also know that n is equal to mr. So let's go ahead and substitute that into here and change our limit. And what we get is this: t equals P times the limit as m goes to infinity of 1 plus 1 over m to the mRt. Now, why on earth did we do that weird substitution? Well, the reason is we have this handy-dandy constant called E that shows up literally everywhere. In science, biology, math, meteorology, pretty much every discipline we have this magical constant, just like pi. And E happens to be the limit as m goes to infinity of 1 plus 1 over m to the m. So let's take this expression for E and let's plug it in here. Now our total is going to be P E to the RT, a very simple solution compared to the other solutions. So just as a refresher, the P is, I'm going to copy this over. If I can figure out how to do that. Bear with me here. Okay. There we go. So P was our principal, R is the annual interest rate, N is the number of times the interest is compounded in 1 year, and T is simply the number of years. So let's see if you can figure out pretty much any math problem involving the total amount of money that you would have after a given number of years with continuously compounded interest with this formula. So let me just reiterate here, and then we'll put in some numbers so we can see how continuously compounded interest is the most advantageous, and also the more often you compound interest, the more money that you're going to have. So let's say that we start out with a principal of $1,000. Let's say an interest rate of 6%, and let's say T is 3 years. So you have the money in the bank for 3 years. Okay. So let's say we compound annually. Our total is simply going to be the principal times 1 plus the interest rate, 0.06, raised to the third, because it's 3 years, okay? And this is going to be 1191.02. So after 3 years, you basically get another $191.02 off of your original amount. And this is compounded annually. Okay, now let's say we compound it monthly. What's this going to look like? Well, now T is our total amount is our original investment plus times 1 plus 0.06 over 12, and then this is times 3 times 12. So in other words, to the 36th power. And I'll just do the calculation here real quick for you. This is going to be 1196.68. So a little bit more if compounded monthly. Okay, now let's see what happens if we continuously compound our interest. So that's 1,000, which is the principal, times E to the 0.06 times 3 years. And this is going to get us 1197.22. And you can see that continuously compounded interest gets you the most overall.